We're going to continue into Chapter 7, and today we're going to talk about molecular geometry, the geometry of molecules. And this is going to go along with what we learned in the last lecture on drawing molecules. We'll be seeing regular molecules, we'll be seeing resonance structures, and we'll be seeing expanded octets. Now we're going to start with molecular geometry, and then we're going to move on to the polarity of molecules. And the reason that we start with molecular geometry is because one of the things that a polar molecule relies on is an asymmetric shape, a non-symmetric shape. So the shapes of molecules is going to tell us a lot about if a molecule is polar or not. Okay, let's go ahead and get warmed up, and then we'll start with molecular geometry. Okay, first, draw Lewis structures of carbon tetrachloride, carbon disulfide, acetylene, and hydrazine. All right, well, for carbon tetrachloride, step one, our central element is carbon. So step one, we draw in our central element. Step two, we now bring in the peripheral atoms to line up with those non-bonded electrons, those free single electrons. And here we have carbon tetrachloride. Do note, if we investigated, we would see that each carbon has 4 electron pairs, 4 8 outer electrons, and each chlorine would have 4 electron pairs, 4 8 outer electrons. For the carbon disulfide, carbon is going to be the element in the middle. When we go to bring in our 2 peripheral sulfurs, we realize we're going to be left with some multiple bonds. Now, how do we know that so early? Because we have more bonding needs. We need to form 4 bonds with carbon. Then we have peripheral atoms to share them with. We only have 2 sulfurs. So we need to form 4 bonds, but only 2 sulfurs. That's our big clue. We must end up with multiple bonds. Okay, so there's step 1 and step 2, and we see those leftover electrons, and so we're going to have a step 3, and this would be our final product. And if we went back and looked, we would see that the sulfurs have 8 outer electrons and the carbon has 8 outer electrons. Again, when we're done, everybody should have satisfied their octet. And that's true for everybody until we get to expanded octets. For hydrazine, for acetylene, carbons go in the middle, and both of them are in the middle, so I have to have a bond holding them together. Let's bring in those 2 peripheral hydrogens. And now I see I have some leftover electrons on those carbons, so let me bring them down to form additional bonds. And indeed, the hydrogens have 2 electrons around them, which is what they want, but each carbon has 8 electrons around them, which again is what carbon wants. In hydrazine, the 2 nitrogens are going to go in the middle, and of course I have to have 1 bond holding them together. Step 2, I bring in my peripheral atoms, and I am going to have a step 3. I have 2 leftover electrons, which need to come together to form an additional bond between those 2 nitrogens. And then again, I can see 2 electrons around each hydrogen, 8 electrons around each nitrogen. And now we're asked to write resonance structures for azoic acid. You may recall this from our last lecture. And here we have the 3 nitrogens in a row with the hydrogen hanging off of one of the ends. So ultimately we would start with something like this. But as you've heard me mention before, we want to keep all of our electrons together in pairs. So let's go ahead and take those free lone electrons and form 2 pairs from them. And when I'm done, I'm going to just go ahead and put one of those pairs on nitrogen number 1. I'm going to call that nitrogen 1, and the other on the nitrogen on the right end, I'm going to call that nitrogen number 3, and let the one in the middle be nitrogen number 2. Okay, now is that one of our structures? No. My first nitrogen has 8 outer electrons, but nitrogen 2 and 3 have 6 outer electrons. Let me go ahead and take that non-bonding electron pair around nitrogen number 2 and bring it down as a bond between it and nitrogen number 3. And at that point, nitrogen number 3 is up to 4 bonds, or 4 electron pairs, for a total of 8 outer electrons. So nitrogen number 3 is okay, nitrogen number 1 is still okay, but nitrogen number 2 only has 6 outer electrons. So what can we do to increase the number of electrons for nitrogen number 2 without reducing the number of electrons for nitrogen number 1 or 3? And here we're going to donate one of those non-bonding pairs from nitrogen number 1 to form a bond with nitrogen number 2. And we can see 2468 around number 1, 2468 around number 2, and 2468 around nitrogen number 3. Okay, for the next example, I'm going to start with where I just left off, and how about we go ahead and give that the second electron pair in that double bond between nitrogen 2 and 3 to nitrogen number 2. So again, I just went ahead and gave that electron pair to nitrogen number 3. And now nitrogen number 1 and nitrogen 3 are okay, but again, nitrogen 2 is 2 electrons shy, so let's go ahead and bring down that last lone pair on nitrogen number 1. So nitrogen number 1 now forms an additional bond, and we see 8 electrons around number 1, 8 electrons around nitrogen number 2, and 8 electrons around nitrogen number 3. Okay, what else can we do? Well, how about we take that electron, and kind of go back to where we were a moment ago. Take that electron pair from between nitrogen 1 and 2 and give it to nitrogen number 1. And then we have 8 on number 1, 6 on number 2, 8 on number 3. So let's go ahead and bring down a second electron pair from nitrogen number 3 to form an additional bond, a triple bond between nitrogens 2 and 3. And at this point we have 8, 8, and 8 electrons around each of those nitrogens. So there are the 3 resonance structures for azoic acid, and this is about as challenging as it's going to get. Normally once you have one, the others just fall right into place. There's a little bit more work with this one. Okay, in nitrosyl chloride, the nitrogen is actually in the middle, and as a minimum we're going to have the nitrogen in the middle, and then an oxygen, and a chlorine bound to it, and so we're going to have one bond between them. If we count all of the outer electrons, nitrogen gives us 5, chlorine gives us 7, each oxygen gives us 6, there's 24 electrons for 12 pairs. So we would have 3 pairs of electrons holding the nitrogen to the 2 oxygens and a chlorine. And then I would start giving those additional pairs to the peripheral atoms as you've seen before. So the 4th, 5th, and 6th goes to the oxygen on the left. 7th, 8th, and 9th went to the oxygen on the top. 10th, 11th, and 12th went to the chlorine. From here now we can see, I think, pretty clearly that everybody's good except for the nitrogen, and so how can we keep everybody where they're at, meaning the peripheral atoms at the number of electrons they are at, yet increase the number of electrons around nitrogen? Yeah, we can do that by dropping one of those lone pairs on one of those peripheral atoms down to form a double bond. And once we have one of these structures, we know that the other one is pretty much the same structure, but the double bond is now going to be between the oxygen on the left and the nitrogen instead of the one on the top. And you may recall me saying before that the chlorine really isn't going to be very conducive to participating in this resonance. To be honest with you, I do believe that it does do some, so that it can be forced into producing that double bond. But it really doesn't want to produce that double bond. We'll find that the larger elements have a harder time forming multiple bonds. Okay, next we have dinitrogen oxide, and nitrogen actually is in the middle, so that makes this a little bit of an oddball. And here is just starting my procedure with my normal approach, and then as you've seen before, I want to get all those electrons into pairs. So let me just go ahead and pair them up. And actually I kind of cheated and went ahead and paired them up in such a fashion that I have 8 electrons around the nitrogen on the left, 8 around the one in the middle, and 8 around the oxygen on the right. I think we can see that I took the 2 electrons that were the 2 free electrons around nitrogen number 1 and went ahead and gave it to it. Took the other 2 electrons that were around nitrogen number 2 and the oxygen and went ahead and made a double bond between the nitrogen and the oxygen with that, and then took that free electron pair on the central nitrogen and formed a second bond between the nitrogen on the left and that central nitrogen. So essentially that's what I did to give me really quickly one of the resonance structures. And let's see, what else can we do? Well, as I move my electrons around, I find that I can arrange them so that I have a triple bond between the two nitrogens and a single bond between the oxygen. And everybody has 8 outer electrons. And can you see what the last one's going to be? That's right. We're now with a triple bond between the nitrogen and the oxygen, and a single bond between the two nitrogens. And it has everybody with 8 outer electrons, and as long as each element has 8 outer electrons, and the central element is not changing its geometry, which essentially means the molecule is not changing its geometry, then this is allowed. If I try to come up with a resonance structure that would change my geometry, then that's not going to happen, because these resonances happen so fast that we don't have time for the atoms themselves to actually move. Okay, let's write resonance structures for sulfur trioxide. Okay, if sulfur is going to go in the middle, I'm going to arrange my 3 oxygens around that central sulfur in a symmetric fashion, so one on the left, one on the right, one on the top. When I count my number of outer electrons for everybody, I have 6 for the sulfur, 6 for the 3 oxygens. This gives me 24 electrons again for 12 pairs. The first of the 3 12 pairs between the sulfur to the oxygen on the left, the sulfur to the oxygen on the top, sulfur to the oxygen on the right, and then I start putting in unshared electrons around the peripheral atoms. So my 4th, 5th, and 6th electron pair would go to the oxygen on the left. My 7th, 8th, and 9th electron pair would go to the oxygen on the top. Nope, that's not what I drew, but that's where I started. My 10th, 11th, and 12th electron pair on the oxygen on the right. But I would have noticed that I only had 6 electrons around my sulfur, and so that's why I donated down one of the non-bonding pairs from one of the oxygens. Did it matter which oxygen? No, and that's what tells us about the different resonance structures. We have this with the double bond between the oxygen on the top and the sulfur. Of course, another resonance structure would be with the double bond between the oxygen on the right and the sulfur. And I think you know what the last resonance structure would be, where the double bond is between the sulfur and the oxygen on the right. And again, with the quick visual inspection, we can see 8, 8, and 8, 8, 8, and 8, 8, 8, and 8 outer electrons around each of those elements. So again, everybody needs to have 8 outer electrons to have us successfully achieved a resonance structure. Okay, you might want to stop and do the rest of these on your own, the nitrite, nitrate ion, and the hydrogen carbonate ion. So why don't you go ahead and do that, and then we'll pick it up from there, and I'll go over the answers. Okay, for nitrite, we are left with a double bond between one of the oxygens on the nitrogen, which means we actually have a lone pair left on that central nitrogen. And of course, we hopefully can see there's going to be a second resonance structure, where in this case it's the other oxygen that had the double bond to the nitrogen. In the nitrate ion, we have the nitrogen bound at least with one bond to each of those 3 oxygens. Once we put all the additional electrons around the peripheral oxygens, we would see we have 8 electrons around each oxygen, but only 6 around the nitrogen, so we had to bring down one of those free electron pairs, very much like we did in sulfur trioxide above. And the other 2 structures are going to be different only in which of the oxygens is donating the double bond. And note, for these ions, I would just go ahead and give that additional electron to somebody. Since we're working with electron pairs, it doesn't really matter what that somebody is. But do count it when you're trying to determine your total number of electron pairs. And here would be one of the resonance structures for the hydrogen carbonate ion. And here would be the other resonance structure. So again, the easiest way, I believe, is to put all the electrons into pairs. First put a pair between the central element and any peripheral atoms. Then start putting in additional electron pairs around the peripheral atoms. When you're done, see if everybody has 8 outer electrons. You may find that the central element doesn't have 8 outer electrons, and one of the free electron pairs is going to have to come down to satisfy that central element. Okay, the Lewis structures for sulfur hexafluoride, xenon tetrafluoride, and chlorine trifluoride. I can see from these formulas that these are going to be expanded octets. How can I see that so quickly? Well, for one, xenon doesn't want to bond at all. And then sulfur wants to bond twice, not 6 times. Chlorine wants to bond once, not 3 times. So those are my clues telling me that I have expanded octets. But if I didn't see that earlier, I'm still going to be okay. There's my step 1. Let's bring in those peripheral atoms for step 2. Oh, I don't have enough single unpaired electrons. There's my big clue. I'm going to have to break open those pairs of electrons so that I have enough bonding potential to essentially bond to those 6 fluorines. And now we can quite clearly see 2, 4, 6, 8, 10, 12 outer electrons around the sulfur that we have an expanded octet. Xenon is the central element in xenon tetrafluoride, and we see we're going to have to break open 2 of those lone pairs in order to form the 4 bonds necessary to bond to the 4 fluorines. In chlorine trifluoride, I have 1 free electron on that chlorine, but I need 3, so I'm going to have to break open one of those additional pairs. I hope you find that Lewis structures for expanded octets is pretty much as easy as Lewis structures for normal molecules, and both are quite a bit easier than resonance structures. Okay, some more expanded octets. Iodine's our central element in iodine pentafluoride, and I need to form 5 bonds, so I'm going to have to break open 2 of those lone pairs. In selenium tetrachloride, the selenium is a central element, and I need to form 4 bonds, so I need 4 single electrons. So again, I had to break open 1 of those free pairs. And we did something very similar earlier between chlorine trifluoride. Here we have bromine trichloride. I need to form 3 bonds, so how am I going to do that? What do I need to do? Break open an additional pair. So again, I took one of those non-bonding pairs and broke it open to form 2 additional free electrons, so I can form those 2 additional pairs. Bonded pairs or covalent bonds. Okay, now that we have learned to draw molecules and we've learned a little bit to get us started, we're ready to talk about the geometry of molecules. Now, to help us predict the geometry of molecules, we use the VSEPR theory, the valence shell electron pair repulsion theory. And you gotta love it when a name tells you everything. Valence shell electron pairs repel each other. We know that like charges repel, and we keep our electrons in pairs, so pairs of these charged particles are going to repel each other, and hence pairs of electrons repel each other. So let's not try to make it as individual electrons repelling, pairs of electrons repel, because we know we have pairs and a covalent bond or an unshared pair. Now, again, electron pairs repel each other, so that means they want to be as far away from each other as possible. Keeping that in mind, we're able to now predict the shapes of these molecules. Now, this illustration shows us, and let's just concentrate on the pictures on the right. These they illustrate an atom with 2 peripheral atoms, a central atom with 3, 4, 5, and 6. So essentially we have 2 regions of electrons around the first one. Those 2 electrons push out and keep those 2 atoms at opposite ends of the molecule for a linear shape. 3 atoms push on each other so that they're as far away from each other, and we're left with a 120-degree bond angle between them, and they actually give us what's called a triangular planar shape. Planar because this molecule would actually be flat. When we have 4 regions of electrons, we see we would have this tetrahedral shape. So here we can see how those electrons are being held as far away from each other as possible, and we're left with a 109.5 degree bond angle. Don't worry about remembering those numbers, but that's not the 90 degree bond angle we might think if we try to represent these molecules in 2 dimensions. The next one in line is a central element with 5 regions of electrons, and the one below it has 6 regions of electrons, and note how these are arranged. When we have 5 regions, we have what's called a triangular bipyramid. So do think of having a 3-sided pyramid on the top, and essentially we have one on the bottom, and hence it's called a bipyramid, or triangular bipyramidal shape. The one on the bottom is kind of like having a pyramid on the top, a regular 4-sided, and a 4-sided pyramid on the bottom, but we already have a name for this, and this is called an octahedron. So I do want you to look at these shapes and look at those names. They're over there in the second column if you need to look at them. We have a linear shape when we have 2 regions of electrons, a triangular shape, a triangular planar shape when we have 3 regions, a tetrahedral shape with 4 regions, a triangular bipyramid shape with 5, and an octahedral shape with 6. Okay, now let's look over here on the left column, AX2, AX3, AX4, AX5, and AX, oh, it's missing a 6. This is the convention of representing these molecules. Now, what this means is the A is your central element, so this really only works when we're talking about one central element. By the way, if you had 2, like 2 nitrogens in the middle or 2 carbons, we would expect that they would both have the same shape around them, so we can still kind of determine the shape at that point. But let's keep it simple. We have a central element and then 2 peripheral atoms, or 3 peripheral atoms, or 4, or 5, or 6. Now, I did say that these could be regions of electrons, and I didn't really distinguish a difference between that and a bond to an atom. If we add a lone pair of electrons, it's still going to take up as much room as a bonded pair. To be honest with you, it actually takes up a little bit more. So if we looked at, let's go to AX4, and let's just take one of those one of those atoms off. So let's look at that atom on the top and replace it with a non-bonding pair. We would still have 8 outer electrons around that central element, but now we have 3 bonded atoms, so it would be an AX3, and 1 lone pair, and that would give us an E. We'll see that notation in a moment, an AX3E, where that would still say we would have 4 regions of electrons, 3 X's, and 1 E, for at the heart of this being the tetrahedral shape. So again, if you have 2 regions of electrons, doesn't matter if they're bonding or non-bonding, at the heart of this you have a linear shape. When you have 3 regions, it again doesn't matter if they're bonding or non-bonding, at the heart of it is a triangular planar shape. For 4 regions, at the heart of any of these is the tetrahedral shape, and for 5 we have the triangular pyramid, 6 the octahedral. And then we'll talk about when some of those regions of electrons aren't a bonded atom. They're going to be a non-bonding pair of electrons, and that's going to come up in a moment. Okay, let's go ahead and I would point out column number 4 gives you some specific examples of these shapes. Okay, now the vast majority of our molecules are going to have a nonmetal with 4 regions of electrons around it. So the majority of the time we're dealing with 4 regions of electrons around the central element, so we're dealing with that tetrahedral shape at the heart of any resulting shapes. Now I say resulting shapes because if I have 4 regions of electrons around my central atom, but only 2 of them give me bonds, well, I'm really just looking at those 2 atoms that are bonded, because that's what was telling me the shape. So here, let's go ahead and look at water, and the illustration on the left shows us the 3-dimensionality of that tetrahedral shape. But if we look at the model on the right, we don't see those non-bonding electrons. So we see this bent molecule. So those non-bonding electrons are there and pushing down on those other bonded pairs so that they don't come out opposite ends. Of course, without those non-bonded pairs, this would be a linear molecule. Water would be a linear molecule. Without a non-bonding pair on ammonia, it would be a triangular planar molecule. But note the presence of those non-bonding electrons means we have 4 regions of electrons, so at the heart of each of these is that tetrahedral. But When we look at the shape of the molecule, we're not looking at the non-bonding electrons, we're just looking at the atoms. And so, again, I hope we can see that with water. We see a bent shape, and with ammonia, we see a triangular pyramid shape. It's a little bit, it's not flat like that other triangular planar shape. I mentioned earlier that a lone pair of electrons actually takes up a little bit more space than a shared pair. So it actually, if we have, and in a moment we will have instances of electron pairs that are shared and electron pairs that aren't, is it going to matter which ones are which when we have different combinations, like two pairs that are shared, two pairs that aren't, and we'll need to keep in mind that those non-bonding pairs actually repel a little bit more than the bonded pairs. I want to go ahead and mention that when it comes to a multiple bond, that this is one region of electrons. So a single bond, a double bond, and a triple bond is one region of electrons. So we treat them pretty much all the same. So a non-bonding pair of electrons, a bonded pair of electrons for a single bond, a double bond, and a triple bond are all one region of electrons. Okay, now let's start bringing in some lone pairs. Well, actually, let's kind of go over what we've already have. We have an AX2 geometry. So the two atoms are coming out opposite ends for a linear shape. We had an AX3 geometry, where those three atoms form what's called a triangular planar shape. So they're all on a plane. We have an AX4 geometry, which gives us a tetrahedral shape. An AX5 geometry gave us the triangular bipyramid shape. And an AX6 geometry gave us the octahedral shape. Okay, so this is only dealing with your central element and peripheral atoms. Well, what if you have some non-bonding electrons? Well, most of the time, well, let me go back to mentioning the majority of our molecules have four regions of electrons around them, so they're going to be based on the tetrahedron. But we may have a non-bonding pair of electrons. So as I just put up here, one of those regions of electrons is now a non-bonded pair, so we have an AX3E geometry. The AX3, the X3 says we have three peripheral atoms, and the E tells us that we have one non-bonded pair. And an example of this was the ammonia we looked at earlier. We have those three bonded that are kind of being pushed down, forming a triangular pyramid shape. Okay, so we can have an AX2E2, and water was an example of this, where we had two atoms that were bonded and two non-bonding pairs of electrons on that central element. And remember, when we looked at just the bonded pairs, we had a bent orientation. But at the heart of this was still that tetrahedron. When it comes to five regions of electrons, we don't have to only have all five going to atoms. We can have four of those regions going to being atoms and one being a non-bonded pair. So this is an AX4E geometry. Now at the heart of this is the trigonal bipyramid. Now when I'm doing this by myself, I'm going to take one hand and open my thumb and my forefinger and my index finger and do the same thing with my other hand, and then put those two hands together, one on top of the other, so that my two thumbs are touching, my two forefingers and my two index fingers are touching, and hopefully you can see that this looks like a triangular bipyramid. So at the heart of our shape is this triangular bipyramid. Now we're going to take away one of these atoms and put in a non-bonding pair. Which one is going to go away? The one on the top, which we call polar, or the ones in the plane, which we would call equatorial. So again, the one out the top and the bottom we would call polar. The ones in the horizontal would be the equatorial. which one is going to go to a non-bonding pair of electrons. Now remember, non-bonding pairs of electrons occupy a little bit more room than a bonded pair, so they want the most room available. Well, what has the most room? Well, the one on the top only has 90-degree bond angles between it and the three in the equatorial plane. The one in the equatorial plane has a 90-degree bond angle to the one on the top, but it has a 120-degree bond angle to the other two in the equatorial plane. That means it actually has a little bit more room in the equatorial plane. So that's where the non-bonding electron pair goes, in the equatorial plane. And if you take that away, you may see, shake your hands back and forth, that you have a seesaw shape. I have a better picture of this coming up here in a little bit, so let me get back to that in a minute. Okay, we can have 5 regions of electrons where 3 are bonded atoms and 2 are non-bonded electrons. And so the 2 that go to non-bonding electrons are going to be in that equatorial plane. So we're left with the 1 out the top, 1 out the bottom, and 1 out the side, which gives us a T shape. We can have, again, 5 regions with 2 atoms that are bonded and 3 non-bonding electrons, and now all 3 of the non-bonding electrons are in the equatorial plane, and the 2 that are bonded are coming out opposite ends, so opposite poles, and that gives us a linear molecule, 1 out the top and 1 out the bottom. Okay, so that's it for 5 regions of electrons. For 6 regions of electrons, we can have 5 that are bonded to atoms and 1 that's a non-bonded electron pair. And now, unlike having 5 regions of electrons around our central element, each of these atoms in an AX6 geometry is in an equal environment. And so it didn't really matter which you took away of those 6. And let's just take one away. Let's take away the one on the bottom, just to make it easier for us to see. And that leaves us with 4 in the plane and 1 at the top, which gives us a pyramid, or your normal pyramid, or a square pyramid. We can have 4 atoms bonding and then 2 lone electron pairs, so an AX4E2. And here we just take out the 1 on the top and the 1 on the bottom, because the lone electron pairs, repelling more than anybody else, are going to come out opposite ends. So we can see no matter how you slice and dice it, they're coming out opposite ends from each other, and that leaves us with a square planar shape. And that would be it for the combinations that also involve electrons. Here's a better picture illustrating those. And so let's just start at the top. Here's our AX5, and then below it, one of those is a non-bonding electron pair. So we have an AX4E. Note how it comes from the equatorial plane. The one's in the middle, or in the horizontal. AX3E2, now we have 2 that were exchanged with electron pairs, so 2 now show up in the equatorial plane. Note how that gives us a T shape. When we had an AX4E, maybe we can see a seesaw shape there. Try to use your imagination of it tilting back and forth on those 2 in the equatorial plane. And then if we have an AX2E3, the 3 non-bonding electrons take position up along the equatorial plane, leaving the 2 out opposite poles for a linear shape. Then below we have an AX6 geometry. There's our pure octahedron. Let's make one of those a non-bonding pair for an AX5E, and let's just give it to the guy on the bottom. It really doesn't matter. You can do it to the one on the left, the right, front, back, top, bottom, and when you're done rearranging them, they're still going to end up looking like this. And that gives us a square pyramidal shape. And we can have 2 that are non-bonding pairs. They're going to come out opposite ends. And again, it doesn't matter if they're the one on the left and the right, front and the back, top and bottom. It's still going to result in a square planar shape. It's just easier to see it when you take it from the top and the bottom. Okay, let's do some examples where we're asked to predict the geometries of, and the first is oxygen difluoride. Okay, well, I see an AX2. Oxygen is my central element, the fluorines are my peripheral atoms, so AX2. Is that it? Well, I expect I might have some non-bonding electrons, so I would begin like this. My central element is oxygen. how many outer electrons does oxygen have? 6. Of those 6, how many is it bonding? 2. So how many aren't bonding? 4. How many pairs of electrons is 4? 2. For an AX2E2 geometry. And you may recall that that is bent. In phosphorus trichloride, our central element would be phosphorus. Phosphorus has how many outer electrons? 5. Of those 5, how many is it used to bond? 3. The 3 going to the 3 fluorines. So how many aren't bonding? 2. How many pairs of electrons is that? 1. For an AX3E. It's easy to see the AX3. We have to do a little bit more work to determine are there E's and how many. And what is the geometry of an AX3E? Well, let's make that tetrahedral shape. So I would take your 3 fingers, your thumb, your forefinger, and your index finger, and then take your second hand and put one finger pointing down into it, and maybe you can kind of see a tetrahedral shape. Let's take away that second hand, which represents that additional pair of electrons, and we see those 3 in a pyramid shape, or a triangular pyramid, sometimes called trigonal pyramid. Okay, next we have the chlorate ion, and when I see oxygens as a peripheral atom, I suspect resonance. So I really need to draw one of these resonance structures before I can tell what the geometry is. And now that I've drawn one, I can see I have an AX3E. I can see I do have a lone pair. Now do note, if I had a double bond instead of that electron pair, I would have an AX3 and no E. So I need to really draw one of these resonance structures when I have one. And I only need to draw one because remember, the shape doesn't change when you have resonance going on. So I just need to draw one. And we can see again, this is an AX3E geometry. And you may remember from the last one, that was an AX3 geometry, and so the AX3E geometry, so this is also a triangular pyramid. And I hope you remember that little trick I showed you with your fingers. Okay, next we have the nitrate ion, and again I suspect resonance, so I need to draw one of these. And when I've drawn one of these, I can see very clearly what geometry do I have. Well, there's no E's, so an AX3. And I might be able to just look at this and see that with 3 regions of electrons around my central element, I have a triangular planar shape. Sometimes drawing these molecules will give you your answer. Is this bend, triangular pyramid, triangular planar, tetrahedral, octahedral, etc., etc., etc. So again, if it's kind of elusive to you what the shape is, try drawing it out. Okay, dinitrogen oxide has one of the nitrogens as a central element, and again I suspect resonance, and so I need to draw one of them, and I'm going to go ahead and draw all 3 just to make my point. What is the geometry of the central element? Well, in the one on the left, AX2, the one in the middle, AX2, one on the right, AX2. So they're all AX2. And they should be if they're resonance structures because we don't have time to change the shape. And AX2 is a linear shape. And again, I think we can look at some of these and see, yep, that's linear. So again, when in doubt or you're having a hard time, draw it. It's going to take a little extra time, but at least this is something you can do to essentially see what it is that you have. And a lot of people are very visual. Okay, now we're in a position to talk about the polarity of molecules because a polar molecule has an unequal distribution of electrons around the central element. Again, the central element has an unequal distribution of electrons. So what does that mean? Ultimately, it means one side of the molecule looks different from another. Or we have a different look from one side to another. There is something different from one side to another, and so I hope we can see how shape is going to be an important part of this. Now, We're going to begin with what are called polar covalent bonds. We know that a covalent bond is two atoms sharing electron pairs, but if we have two atoms with different electronegativities, remember electronegativity, the tendency of an atom to attract additional electrons. If you have a low electronegative element and a high electronegative element, that high electronegative element is going to strongly pull those electrons in that shared pair closer to itself. And in doing so, the more electronegative element takes on a slightly negative charge, and the less electronegative element is now missing electrons, and so it takes on a slightly positive charge. And here we can see a few examples. The one on top, beryllium difluoride. The atom in the middle is beryllium, which is way less electronegative than the two fluorines. And so do note we have these arrows with a plus on one end. What we see with this convention is the arrow points towards the more electronegative element, or essentially it points towards the negative side. So in that bond, we have the greater amount of electrons on the fluorine sides and the lesser amount on the beryllium side. So essentially the positive lines up with the positive end, and the arrow points towards the negative end of that polar covalent bond. And what are the oxygen is the most electronegative element, so that's why the two hydrogens are arrows pointing towards the oxygen, because the arrows point towards the negative side of that polar bond. The positive side essentially is the positive end, or the positive atom in that polar covalent bond. Here we see carbon tetrachloride. Chlorine is more electronegative, so the arrows are pointing towards the chlorines. The one on the bottom right is, this is actually chloroform. That's actually the trivial name for trichloromethane, but anyway, the arrows point towards the chlorines with the carbon-chlorine bond, but it points towards the carbon with the hydrogen the hydrogen-carbon bond, because carbon is more electronegative than the hydrogen. Now, I want to just give you something to think about. Of these four molecules, which are polar and which are nonpolar? Well, when I look at the one on the top left, it's totally symmetric. And even though I have a negative end on the left, I also have a negative end on the right. So I don't have one end different from the other. And if they are symmetric in this fashion, then essentially those polarities cancel. And this is a nonpolar molecule. So that beryllium difluoride is nonpolar, even though we have very polar bonds. What about water? And I think we can see by looking at this is an asymmetric shape. The top of the molecule isn't the same as the bottom of the molecule, and so we do have one end looking different from the other, and so this would be a polar molecule. The third example, carbon tetrachloride, again, very symmetric arrangement of those bonds, so that symmetry is going to cancel the polarity. So carbon tetrachloride was also be nonpolar. Now, what about the chloroform, the trichloromethane? I'm giving you two names because there are two names. One's trivial, one's systematic. Well, do note that now the top of the molecule doesn't look at all like the bottom of the molecule. One end looks different from another, and so we can see how that's also a polar molecule. So the two molecules on the left were nonpolar because of symmetry. Two molecules on the right are polar because of their asymmetry. Well, actually, two things, polar covalent bonds and asymmetry. Okay, so this leads right into what I just said. If you have a symmetric distribution of electrons around your central element, you have a non-polar molecule. Even if you have very polar bonds, you still have a non-polar molecule. Now we have polar molecules, sometimes called dipoles, when we do have this asymmetric distribution of electrons around the central element. So that means you have an asymmetric shape, and you have polar covalent bonds. So again, a polar molecule, one side of the molecule is different from the other. And no matter what that difference is, it's going to lead to a difference in electrical distribution. So again, any difference is enough to tell us that this is polar. Okay, in hydrogen fluoride, we have a polar molecule, and I didn't do a good job of making an arrow with a plus on the back side. That's what that's supposed to be. Remember the plus on the back side. The plus is going to line up with a positive atom, and the arrow points towards the negative atom. And as we saw earlier, sometimes we may have these polar bonds, but we have a symmetric orientation of them so that one side looks just like the other, and ultimately what that means is all those polarities would cancel and we're left with no leftover polarity to the molecule. So again, the two on the left are nonpolar because of their symmetry. The two on the right are polar because they have asymmetry. Now, I've kind of alluded to the two requirements to be a polar molecule, and the first is you have to have one or more polar covalent bonds, and that's one that's easy to spot. If you have a compound, you have polar bonds. So if you have two or more different elements in your formula, you have polar bonds. So only elements like O2, N2, I2 would be non-polar bonds, meaning actually they're normally called pure covalent bonds. They wouldn't be polar because they're shared between two identical elements. But once you bring in two different elements, we have a polar covalent bond. Even if it's just a little bit of a difference between their electronegativity, there's still some polarity to their bond. So again, that's the one that's real easy to spot. Two different elements in the compound, meaning it is a compound, and then you have at least one polar covalent bond. And then the second is it must be asymmetric. So it has to have a asymmetric shape. Now, let me just mention a few things, and I'll mention them again as we go through some examples. If you only have one thing attached to your central element, it's always going to be arranged symmetrically. So if I have a carbon with just chlorines attached, they're going to be arranged symmetrically. Just hydrogens attached, it's going to be symmetrically. Just oxygens attached, it's going to be arranged symmetrically. Now, if I have two or more things attached, maybe I have a carbon with an oxygen and a sulfur, two or more different things attached, that ruptures your symmetry, and that would then mean you would have an asymmetric molecule. Now, there's a couple of exceptions to that, really only two, and I'll go over those in a little bit. But there is no exception to if you only have one thing attached, it's always symmetric. Only hydrogens attached to my central element, symmetric. Now, do note, you need to take into account non-bonding electrons as well. Non-bonding electrons would be a something. So if I have, let's see, how about oxygen? Well, let me do sulfur. If I have sulfur with two hydrogens attached, but I also have two non-bonding pairs of electrons, well, that's two different things. So don't just look at the formula, because the formula doesn't tell you about the non-bonding electrons. Okay, we already saw examples where water and ammonia were polar because they had that asymmetric shape. We had two different things attached. We had non-bonding electrons. Whereas the carbon tetrachloride was a non-polar molecule, even though we had polar bonds, because we only had one thing attached, those chlorines, they were arranged symmetrically. And it doesn't matter how polar your bonds are. If you have a symmetric molecule, it's going to be a non-polar molecule. And there are two pictures illustrating water and ammonia and the asymmetry of their shapes due to having two different things attached. And in the bottom left is the carbon tetrachloride with a very symmetric shape because we only had one thing attached. Just like above it in beryllium difluoride, a very symmetric shape because we had one thing attached. So why aren't water and chloroform symmetric? Because they have two or more different things attached. So again, one thing attached, doesn't matter how you slice and dice it, it's always symmetric. Two or more things is required to be asymmetric. Okay, let's go through some examples to determine whether the fluorine is polar or nonpolar. And sulfur dioxide, I hope you are already thinking resonance. Remember, if you got a central element with two or more oxygens attached, expect resonance. So we need to draw one. Once we've drawn one, we can see there's our shape. We have an AX2E geometry, which is an asymmetric shape. And since we have polar bonds in an asymmetric shape, sulfur dioxide is polar. Okay, for beryllium trifluoride, first, do we have polar bonds? Yep, easy to spot, two different elements. Let's see, boron's our central element, and boron doesn't have any outer, non-bonding electrons. It has just the 3 outer electrons that it used to bond. And if you only have one thing attached, what does that tell us? That it's symmetric. And it doesn't matter if we have polar bonds or not. If it's symmetric, it's nonpolar. Okay, in carbon dioxide we have polar bonds. And if I draw the molecule, I can see that central element has just those 2 oxygens. I don't have any leftover non-bonding electrons. Only one thing attached means symmetric. And symmetric always means non-polar. So let's just look at that carbon dioxide. While we have very strong pull to the left, meaning the oxygen is trying to attract electrons, we have that same strong pull to the right. And so we're just as negative on the left as on the right. The left looks just like the right. So that's why I say one side looks different from the other. And in this case they don't. That's why this was nonpolar. But we can see in the one at the top that it doesn't look symmetric, that they have 2 or more different things attached, and hence it was polar. Okay, let's practice some of the things that we have just learned. Predict the geometries of, well, let's see. First, my central element would be the iodine. I'm going to give it that extra electron, so it would have 8 outer electrons. 2 of them are being used to bond, so there is 6 that aren't. 6 electrons would be 3 non-bonded pairs. In other words, we have an AX2E3 geometry. 5 regions of electrons. Let's put our hands together to form that trigonal bipyramid. And where do the lone pairs show up? In the plane. So there goes 1, 2, 3. So all 3 in the plane went away, leaving me 2 out the opposite ends. And hence I have a linear geometry. So do know, we can use the Vesper theory and the things that I've taught you here today to predict these shapes. We don't just need to simply memorize an AX2E3 is linear. We can see this by recognizing what that means, what that valence electron pair repulsion is doing, what shape is left. And again, it also requires us to remember that non-shared pairs take up a little bit more room than shared. That's why they wanted to be in the plane and not out each pole. Okay, in radon tetrafluoride, radon is our central element. Radon has 8 outer electrons. 4 are being used to bond. So 4 aren't, and hence we have an AX4E2 geometry. So again, 4 non-bonding electrons meant 2 pairs. And I see 6 regions of electrons around my central element, so at the heart is the octahedral. And we take away the electron pair at the top, the electron pair at the bottom, and I hope we can now see what's left is a square planar shape. Sulfur dioxide, what do you suspect? Resonance. So let me draw one. Now I can see an AX2E geometry. I hope you can see from the drawing AX2E, 2 atoms, 1 lone pair. And that gives us a bent shape. These are all triangular planar, but take away one of them, and what's left is a bent or angular shape. Okay, in selenium tetrachloride, selenium is a central element. Selenium has how many outer electrons? 6. 4 being used to bond, so 2 aren't for 1 non-bonding pair. And hence we have an AX4E. I see 5 regions of electrons, the 4 X's and the 1 E. So again, let's put our fingers together to form that trigonal bipyramid. And now, where does that E go? That's right, in the plane. And now let's shake our hands back and forth to help us remember what shape is that. Seesaw. In phosphorus pentachloride, phosphorus is a central element. Phosphorus has 5 outer electrons, and all 5 are used to bond. And so we have an AX5 geometry, 5 regions, all going to atoms, our triangular bipyramid. Okay, same question for krypton difluoride. Krypton's the central element, has 8 outer electrons. 2 are being used to bond, so that's 6 that aren't. 6 electrons is how many pairs? 3. So an AX2E3 geometry. That's 5 regions electrons. So again, let's hold our 2 hands together to show our trigonal bipyramid, and the 3 electron pairs disappear from the equatorial plane. So 1, 2, 3 disappear. The 2 that are left come out opposite poles. And that then is a linear geometry. Now, this is one of the instances where you can have a non-bonded pair of electrons and still have a symmetric shape. With the exception of an AX2E3 and an AX4E2 geometry, I'll go over the other one in a minute, any other instance, if you have electron pairs, it's going to be asymmetric. There's only 2 instances when you do have electron pairs and it's symmetric, and that would be AX2E3 and AX4E2. We'll talk about this some more, so don't worry about writing that down. Okay, next we have sulfur hexafluoride. Sulfur is our central element. Sulfur has 6 outer electrons, and it's using all 6 to bond to the 6 fluorines. Hence an AX6 geometry. 6 regions of electrons is an octahedral, and all 6 are going to an atom. Bromine trichloride. Bromine is the central element. Bromine has 7 outer electrons. 3 are being used to bond. That's 4 that aren't, or 2 electron pairs. I see 3 regions of electrons around our central element. Let's put our 2 hands together to form the trigonal bipyramid, and 2 of those in the plane disappear. So we have 1 out the top and the bottom and 1 out the side, and that is a T shape. Next we have the sulfite ion, and I suspect resonance. I need to draw one. And there is one, and I see I have an AX3E geometry. And I can actually see from the picture that this is a triangular planar shape. So imagine I have that 3-sided pyramid. Remember that 3 electron pair is pushing down on those 3 shared pairs to get this shape. Okay, this is the thiocyanate ion. Carbon goes in the middle, and it has 4 outer electrons. I'm going to have, well, essentially of those 4 outer electrons, all 4 are used to bond, and so no non-bonding pairs. I'm going to go ahead and draw one just to help me see it. Plus I might suspect resonance. And here I can see I have an AX2 geometry, and an AX2 geometry gives us a linear shape. And again, I think we can see the linear shape from the illustration. Okay, determine whether each of the following is polar or non-polar. Okay, first, what is the geometry of that molecule? Well, iodine is the central element. Let's give the extra electron from to the central element, meaning give that outer that electron from the charge, that extra electron from the charge to the iodine. So it has 8 outer electrons. 2 are being used to bond, so that's 6 that aren't, for an AX2E3 geometry. And is that a symmetric shape? And that is one of the 2 examples where you have non-bonding electrons where you still have a symmetric shape. And symmetric means non-polar. And radon tetrafluoride. Radon's the central element. First we have polar bonds. 2 different elements, we got polar bonds. We got a compound, we got polar bonds. And radon's essential element, 8 outer electrons, 4 are being used to bond, so 4 aren't, so that's 2 electron pairs, so an AX4E2. And this is the other example where we have non-bonding electrons in an asymmetric shape, because the first non-bonding pair of electrons comes out the top, the second comes out the bottom, and that leaves us with the square planar shape, which is symmetric. And again, if it's symmetric, it doesn't matter how polar your bonds are. This is going to be a non-polar molecule. So again, with these two exceptions, an AX2E3 and an AX4E2, every other time if you have an electron pair or more, it's going to be an asymmetric molecule. So again, with these two exceptions, any molecule with non-bonding electrons is going to be asymmetric. These are the two only instances where you have a symmetric shape involving non-bonding electrons. The majority of the time, it just gives you a rupture to your symmetry. Okay, for sulfur dioxide, we suspect resonance. First, we have polar bonds. Since we suspect resonance, let's draw one of these, and we can see AX2E, which is a bent geometry, which is asymmetric. And hence sulfur dioxide is polar. Again, to be polar, you have to have polar covalent bonds and an asymmetric / non-symmetric shape. Why don't you take a moment and do the rest on your own, and then bring me back when you have done so. Okay, in selenium tetrachloride, selenium's a central element, and it has 6 outer electrons. 4 of those are being used to bond, so there's 2 that aren't, for 1 non-bonding pair, for AX4E. I have 5 regions of electrons around my central element. Let me put my hands together and take away one of those non-bonding pairs in the equatorial plane. And as I shake my 2 hands, I'm reminded that this is a seesaw shape. Is that symmetric? No. So is selenium tetrachloride polar? Yes. Again, polar covalent bonds and an asymmetric shape are the 2 requirements to be a polar molecule. Okay, in phosphorus pentachloride, we have polar bonds. Oops, phosphorus and chlorine are 2 different elements. The central element is phosphorus. It has 5 outer electrons. All 5 are being used to bond. So this is an AX5 geometry, and that was our triangular bipyramid. And is this symmetric? Well, once again, you only have one thing attached, and that's always going to be symmetric. Again, if there's only one thing attached, only one atom, remember, non-bonding pairs of electrons are a thing. So if you have just one thing attached, so in this case, only chlorines, it's going to always be arranged symmetrically. And symmetric always is non-polar. A little bit of practice goes a long ways with this. Identify your geometry, and that tells you if it's polar or non-polar. And we need to identify the geometry for other work problems. Okay, continuing on. Is this polar or non-polar? Well, krypton difluoride has polar covalent bonds, 2 different elements. Krypton is the central element. It has 8 outer electrons. 2 are being used to bond, so that's 6 that aren't. 6 electrons is 3 non-bonded pairs. So an AX2E3 geometry. I see 5 regions of electrons around it. AX2E3, the 2 and the 3, 5 regions. So there's my 2 hands coming together to form the trigonal bipyramid, and those 3 electrons come away from the plane, giving you a linear shape, the one out the top and the one out the bottom, which is symmetric. Again, an AX2E3 is one of the 2 that the 2 shapes that's symmetric and yet has non-bonding electrons. Any other instance of non-bonding electrons is going to rupture the symmetry. AX2E3 will be symmetric. AX4E2 will be symmetric. Any other account with E's asymmetric. Okay, sulfur hexafluoride has polar bonds. Sulfur is a central element. 6 outer electrons. All are being used to bond. So this is an AX6. This is an octahedral shape, but we really don't even need to look at that to see only one thing attached, and hence sulfur hexafluoride is symmetric. And if it's symmetric, sulfur hexafluoride is nonpolar. So again, symmetric always means nonpolar. Okay, in bromine trichloride I have polar bonds. Bromine's a central element, 7 outer electrons, 3 are being used to bond, 4 aren't, that's 2 electron pairs, so AX3E2. The 2 come away from the equatorial plane. Let's put our hands together or take the 2 away from the equatorial plane, and so we have 1 out the top, 1 out the bottom, and 1 out the side for a T shape. Is that symmetric? No. So is bromine trichloride polar? Yes. For the sulfite ion, I suspect resonance. I can already see I have polar bonds, but I need to draw to see what is the geometry around the central element. And now I can clearly see an AX3E, which is a triangular pyramid. Is that symmetric? Well, I see electron pairs. Is this one of those 2 with electron pairs that's symmetric? No, that's AX2E3 and AX4E2. This isn't one of those, so just by seeing the electron pair, I know this is asymmetric. And if it's asymmetric, then the sulfite ion is polar. Okay, I have 3 different elements here, so I definitely have polar bonds. I'm going to go ahead and draw this. And now I have an AX2 geometry, which is linear. Is this symmetric? Well, linear is normally symmetric, but the guy on the left and the guy on the right are not the same guy. So I don't have just one thing attached here. Like I said, normally if you have 2 or more things attached to your central element, they're going to be arranged in an asymmetric fashion. And hence this is a polar molecule. And I think we can look at that and see, yep, the left side looks different from the right side. If the left and the right were both S's or both N's or both O's, well then we would see, yeah, the left looks like the right and it's symmetric. But those 2 different elements made it asymmetric. Okay, that concludes this lecture on the geometry of molecules and the polarity of molecules. And do practice your AXE nomenclature, or essentially get yourself used to that type of designation. And then remember, polar molecules have at least 1 polar covalent bond, which means 2 different elements. That's the easy one, and an asymmetric shape. And again, we're going to go back to those shapes to tell if it's symmetric or not. And that concludes today's lecture.